So this is class number 5 for the course Climate Data Science, and in the first two classes we saw introduction, like just a flavor of what is data science, and we discussed some state of the art algorithms. And in the last two classes we were going through the material from deep learning specialization, and we have covered the first two courses, neural networks and deep learning and improving deep neural networks. So today we will talk about the third course, which is structuring machine learning projects. And I will try to make sure that if we can cover convolution neural networks as well after we are, so this we will try for the in the first half of today's session. And after we are done with this with the theory session, so we will move ahead with the hands-on in TensorFlow. So we'll go through the official TensorFlow tutorials. Okay, so this course is called Structuring Machine Learning Projects, and it's moderated by deeplearning.ai, taught by Andrew Ng. And in this course, you will learn how to build successful machine learning project. So some tricks of the trade, and if you, so this will show you how you can do your, or the direction, give you the direction in a deep learning or machine learning project. And so Andrew says that this much of this content has never been taught elsewhere and is drawn from his experience building and shipping many deep learning products. So this course has two flight simulators that lets you. So this is about the assignments that he's talking about. So there are these are the assignments in this course, and it will enable you to understand how to diagnose errors in a machine learning system, be able to prioritize the most promising directions for. Okay, I'm sorry, I think I'm not sharing the screen, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
You guys should tell me.
I thought it's just
Okay,
introduction.
so I'm no, I'm sorry about that. So okay, yeah, it's visible now, right?
Yes.
So yeah, so this course will make you understand how to diagnose errors in a machine learning system, be able to prioritize the most promising directions for reducing error, and understand the complex machine learning settings such as mismatch training and test sets, and comparing to and or surpassing human level performance. So in the end, you will, like, the aim is to give you a flavor of how to apply an end-to-end deep learning to your project, perform transfer learning or multitask learning. And so he says that people waste lots of time not understanding the principles taught in this course, and the hope is that this will save a lot of your time when you are actually doing hands-on to your specialized projects. So why machine learning strategy? So you have a lot of ideas on how to improve the accuracy of your deep learning model. So the first is you can collect more data, you can collect more diverse training set, train the algorithm longer with gradient descent, try a different optimization algorithm, try a bigger network, try a smaller network, try dropout. We discussed dropout as a strategy, as a regularization strategy, wherein you would randomly switch off some of the neurons of the deep neural network, add L2 regularization, or change the network architecture. And this course will give you some strategies to help analyze your problem to go in a direction that will help you get better results. So then we have the concept of orthogonalization, and so he says that some deep learning developers know exactly what hyperparameter to tune in order to try to achieve one effect. This process is called orthogonalization. And in orthogonalization, you have some controls, but each control does a specific task and doesn't affect the other controls. So for a supervised learning system to do well, you usually need to tune the knobs of your system, basically try the different hyperparameters for your machine learning model. And you also, so you have to make sure that so to make sure that four things hold true. So you have to, first is you have to fit training set well on the cost function. So that is the first thing that you'll do. And for his case, like for it's problem specific whether you reach a near human level performance or not. So for our case, wherein we would use geoscience or climate science or weather science data sets, we I think we don't need to worry about this aspect. And if it's not achieved, so you could basically plot the cost function while training. And you if you are not able to if you're not able to converge or lower your cost, then you can basically try a bigger network or a different optimization algorithm like Adam. So the second thing is that your your dev set should fit set well on the cost function. So you should ensure that, so the dev set is the during the time of training you have the dev set, which is also known as the validation set. So that should fit well. So you should minimize the cost on your dev set, cost function on your dev set at the time of training. And eventually your test set performance should also be good. So, and the final thing is, if you deploy this model in a real world, it should perform well. Now there are different evaluation metrics. And so what he calls is, like, the title is of the next topic is single number evaluation metric. And he says that it's better and faster to set a single number evaluation metric for the project before you start it. And so there is a difference between precision and recall. I think you already must be aware of the confusion metrics from your statistics course. So on so in the along the rows, so you have the actual. So if you have a binary classification problem wherein you are trying to find out cats and non-cats, so on this, the first row, it corresponds to actual number of cats. The second row is actual non-cats, and then the first column is predicted cat, and the second column is predicted non-cat. So this is the so three is the number of cats which are predicted as cats and actually they were cats, and one is the number of cats which were predicted as cats but actually they were not cats. And so two similarly was predicted as non-cat but it was a cat. And similarly the four was predicted as non-cat, so but it actually was also non-cat. So three, uh, this number and this number we want to maximize, and these two numbers we want to minimize to enhance our performance. So the precision is the percentage of true cats in the recognized result. Okay, so the percentage of true cats, that is what your model has predicted, divided by the like what the total it has predicted as cats. So your model is predicting four cats, out of which three are correct. So you have to just consider your model predictions. And recall is basically percentage of true recognition cat of all the cat predictions. So you have to see all the actual number of cats. So that is basically 5, and you have to see out of them how many are predicted correct. So in precision, you can think of like you go along the column, and in recall you go along the row. So precision is 3 divided by 3 plus 1, and recall is 3 divided by 3 plus 2. And what is the accuracy? So the accuracy is, so the total number of cats here is 3 plus 2 5 plus 4 9 plus 1 10. So accuracy is the total number of correct predictions. So the total number of correct predictions is 3 plus 4 7. Total number of cats is 10. So the accuracy here is 70%. And so using a precision or recall for evaluation is good for a lot of cases, but separately they won't tell you which algorithm is better. For example, classifier A and B. So for A and B, for A the precision is 95%, recall is 90%, but for algorithm B, the precision is 98%. So in this case, the precision is higher, but the recall is lower. So a better thing is to combine precision and recall. So since it's separately it's difficult, or you can't identify which algorithm is better. So you can combine both of these numbers or metrics, and this is known as the F1 score. So F1 score is a combination of precision and recall, which is equal to 2 divided by 1 by P plus 1 by R. So where P is your precision and R is your recall. And then it's, so he says that it's hard sometimes to get a single number evaluation metric. For example, the classifier A, F1 score is 90%, and the run times or the training time is 80 milliseconds. The for the classifier B, your F1 score is 92%, and your runtime is 95 milliseconds. And for classifier number C, or the algorithm C, the F1 score is 92%, but your runtime is much higher. It's 1500 milliseconds. So we can solve that by choosing a single optimizing metric and decide what other metrics to are satisfying. Example, we can maximize F1 subject to a runtime of less than 100 milliseconds. So as a general rule, we maximize one optimizing metric subject to n minus one satisfying metrics. Now, after that, he discusses about the train, dev, and test distributions. So dev and test sets have to come from the same distributions. You have to choose dev set and test set to reflect the data you expect to get in the future and consider important to do well on. So something which would come in future, or something which you care about, that you have to choose as the dev set or test set. And setting up dev set as well as validation metric is really defining what target you want to aim at. So yeah, I mean, what is it that in the ideal world, what that you want from your model? So that basically depends upon how you choose your dev set and the as well as the validation metric. And now we already discussed this. So the size of dev and test sets. So an old way of splitting would be 70% training, 30% testing, or 60% training, 20% dev, 20% test. And so this was valid for a particular number of examples, maybe 100,000. But in the modern day deep learning, if you have million or more examples, a reasonable split would be 90%, 98% training, 1% dev, and 1% test set. So when to basically change the dev or test sets and the metrics. Uh, so let's, if we see from the example of cat classification. So you can see that the algorithm A, it has got a 3% error, and so but a lot of images are treated as cat images here. And algorithm B, it has got 5% error. So which of the algorithm you would consider is would be to be good? So if you choose the best algorithm by metric, it would be A, but if the users decide, that would be B. And thus in this case we want you, so the you should change your metric. And so you can see that the old metric is equal to 1 divided by m, which is the total number of samples, into sum of y pred I not equal to yi comma m. So you would sum over all the wrong predictions. And so you would, so this was your old metric. And your new metric you would define by so you would weight with the images where your predictions are going wrong. And so you would say, so wi is equal to 10 if the image is being so if a lot of porn images are being also treated as cat images. So you would basically penalize your evaluation metric and increase it. So that is what is being done here. And this is an actual example of orthogonalization, where you should take a machine learning problem and break it into distinct steps. So to figure out how to define a metric that captures what you want to do, you have to place a target and then worry about how to actually do well on this metric. So it's a lot of iterative process. You would have to do back and forth and see how your model is performing, why is it performing good or bad, what is the comparison between two models, and whether there is a realistic improvement in performance based upon the what the metric is telling us. So you have to shoot or aim accurately at the target. And if you're doing well on your metric plus dev test set, so doesn't it means you're like, although it means you're doing good for most of the cases, it doesn't correspond to doing well in your might not correspond to doing well in your application. And you might need to change your metric or dev or test set. So then he talks about human level performance. So says that he talk about human level performance for two reasons. And because, so first reason is because of the advances in deep learning, machine learning algorithms are certainly working much better. And so it has become much more feasible in a lot of application areas for machine learning algorithms to actually become competitive with human level performance. So that's why a lot of computer vision papers these days would use human level performance as a baseline or as a benchmark. And then also it turns out that the workflow of designing and building a machine learning system is much more efficient when you're trying to do something that the humans can also do. And after human level performance has, so algorithm reaches that performance, the progress and accuracy actually slows down. So you can see here, the blue line is the what the accuracy of humans is. For example, in finding out whether the image has a cat or not, and the purple is our machine learning algorithm. And he says that you won't surpass an error that is also known as the Bayes optimal error. So there isn't much error between human level error and Bayes optimal error, and humans are quite good at a lot of tasks, but most likely not in our field, geosciences. Like you can't just see and tell. The problems are much more complex. So, and as long as machine learning is worse than humans, so he says that you can get the data labeled from humans. So by humans, what we can consider is the domain level experts or the domain experts. So for example, you are applying a machine learning algorithm to a problem in atmospheric chemistry. So by human level expert, what we mean is a domain expert who knows who knows a lot of science, or who knows a lot of chemistry, the chemical equations, or like how maybe in the stratosphere the the reactions are happening, which are then indirectly affecting the things that are happening in the on the land or on the troposphere. So we have to get the labeled dataset from those experts and gain insight from manual error analysis. So they would be able to tell us how and why our model is performing good or bad, whether the performance is whether one thing is the good result should not come because of the wrong reason. So it might just be a chance that your model is performing good. So the domain experts would be the best people to tell about that, and then a better analysis of bias or variance. So we need to check how much is the bias in our data set, whether the model is underfitting, whether there is high bias, and what is the kind of variance that is there. So you what you would do is you would track the training error or training cost and the validation or dev cost, and then until the time the training error comes down to the validation or dev error, so until that time your model is underfitting. And if your training error is much lower than your dev error or the test error, then that means your model is overfitting or there is a high variance in your model. So there are some of the bias which can be avoided. So that's what we call as the avoidable bias, and that is equal to the training error minus the human or the base error. So yeah, I mean these are going into too much of details on in the computer vision community, so we'll skip these things. And so there are two fundamental assumptions of supervised learning, and so first one is that you can fit the training set pretty well, and this is roughly saying that you can achieve a low avoidable bias. So you can basically get to that optimum number or get to that optimum training where you have a low bias, and you would also want your model to generalize well over the dev or test set. So this is roughly saying that the variance is also not too bad. So there are various guidelines that you can follow to improve your deep learning based system. And so the first one is to look at the difference between human level error and the training error. So which is the avoidable bias, so which is what you can avoid, or you can basically fill the gap. At least you can reach up to the level of the domain expert or the humans. And you can also look at the difference between dev set error, dev or set test error, and the training set error. So that's what we call as the variance. And if avoidable bias is large, so that means that you are underfitting. You need to train either a bigger model or you need to train longer with a better optimization algorithm like momentum RMS prop, or a combination of momentum and RMS prop, which is Adam optimizer. Or you would need to do hyperparameter tuning, find a better neural network architecture, do hyperparameter search. And if you have a high variance, then what you would typically do is get more training data. You can do what you can do is regularization. You can do an L2 regularization, dropout regularization, or you can do data augmentation. And what you can another thing that you can try is find better neural network architecture, or you can do a hyperparameter search. So you can tune the model for the various hyperparameters. And then there is another section which is on ML strategy number 2 that Andrew discusses. So the first one is carrying out error analysis. So you would analyze the errors in your at the time of training or the validation and test error. So you can process. So the process of manually examining mistakes that your algorithm is making. And for example, in the CAT classification example, if you have a 10% error on your dev set and you want to decrease the error, so that's like one particular example, and you discover that some of your mislabeled data sets are dog pictures that look like cats. So should you try to make your classifier do better on dogs? And so the error analysis approach is to get 100 mislabeled dev set examples at random. So what are these 100 mislabeled examples? So which have been labeled or predicted wrongly by your model. Then you can count up how many are dogs. So if 5 of 100 are dogs, then training your classifier to do better on dogs will decrease your error up to 95 up to 9.5%. So and which can be too little. So if 50 of so from 10% you will decrease up to like you can reach up to 9.5%, only in the case if you count the dogs as 5. But if there are 50 dogs out of 100, so basically what we are talking about is so 100 mislabeled examples, but out of those mislabeled examples there is a particular class which is occurring very commonly. And if 50 of those 100 are dogs, then you could decrease your error rate by like, and you can reach up to 5%, which is reasonable, and you should work on that. So basically the idea is that manually going ahead and visualizing or plotting your results, that can be very useful. And so the based on the last example, so he says that the error analysis helps you to analyze the error. Am I audible?
Yes, sir.
Hello?
Yes, yes,
Yes.
yes, sir.
Okay.
Yes, sir.
So he says that, yeah, so thank you. Yeah, so he says that based on so the error analysis helps you to analyze the error before taking an action. That could take a lot of time with no need. And sometimes you can evaluate multiple error analysis ideas in parallel and choose the best idea. So you can create a spreadsheet or an Excel sheet. So in this example we have seen how you can work on the cat classification problem by visualizing or by plotting, manually doing error analysis to improve the performance. And this quick counting procedure, so which you can most often do, can really help you make much better prioritization decisions and understand how promising different approaches are to work on. So this was carrying out the error analysis. The second is cleaning up incorrectly labeled data. So DL algorithms are quite robust to random errors in the training set, but less robust to systematic errors. So there can be some kind of systematic errors as well, like you have labeled your data set wrongly. It's a cat in the image, but you have labeled it as a dog. So they say that they are robust to random errors, but not these systematic errors. But it's okay to go and fix these labels if you can. If you want to check for mislabeled data in the dev or test set, you should try error analysis with the mislabeled column. So example, you can have the first column as image, and in the second column you can see, okay, so whether it's a dog, great cats, blurry, mislabeled comments. So if the overall dev set error is 10%, then errors due to incorrect data, for example, if are 0.6%, then errors due to other causes are 9.4%. Then you should focus on the 9.4% error rather than the error due to incorrect data, because you can't do anything about that. Your input itself is coming with a error in a way that your labels themselves are not correct. Some of the labels are not correct, and there are various guidelines to apply when correcting the dev or test mislabeled examples. So one of them is to apply the same process to your dev and test set to make sure that they come from the same distribution. and then considering examining examples, so your algorithm got right as well as what your algorithm got wrong. So you manually go ahead and examine those results, visualize them. That will give you a better idea and confidence on the results of your model. And then so that they may now come from slightly different distributions, and it's very important to have them come from the same distribution. And build your system, iterate it. So you do bias variance analysis, error analysis, and build the initial system quickly, and set the dev and test sets, and decide on your metric to on which you're trying with which you are trying to minimize your cost on. And then there is some advice on what to do when training and testing is done on different distributions. So he says that a lot of teams are working with deep learning applications which have training sets that are different from dev or test sets due to the hunger of deep learning to data. And there are some strategies to follow up when training set distribution differs from dev or test set distribution. Option one, which is not recommended: shuffle all the data and randomly extract training and dev or test sets. So one is like, if your training and dev or test sets are not coming from the same distribution, you just randomly shuffle. The advantage is that all the sets now come from the same distribution. The disadvantage is that the other distribution, the real world, that was in the dev or test set, will occur less in the new dev or test set, and that might be not what you want to achieve. So you might not get the right kind of results, or you might not be able to get the optimum model that you are trying to get. The second option is to take some of the dev or test set examples and add them to the training set. And so this is like you are deliberately just bringing some of the samples from the dev or test set and adding it to the training set. And the distribution that you care for now is your target in the training data. And the disadvantage is that the distributions in training and test set are now different, but you want better performance over long time. So yeah, so then the next advice is on bias and variance with mismatched data distributions. So if the distributions are different, so how would you do bias variance trade-off? And so bias and variance analysis changes when training and dev or test set are from different distribution. For example, in the CAT classification problem, suppose you have worked in the example and reached, so human error is 0%, training error is 1%, dev error is 10%. So in this example, you'll think that this is a variance problem because your training error is much lower and your dev error is higher. So your model is maybe overfitting. That's what you might think. But because the distributions aren't the same, you can't tell that for sure. And because it could be that the training set was easy to train on, but the dev set is more difficult. That might be the reason. It might not entirely mean that you're overfitting on your training data. And to solve this issue, we create a new set called train dev set. So you basically which you set as a random subset of the training set. So that, and maybe if you now you get the human error is 0, training error is 1%, train dev error is 9%, dev error is 10%. So now we are sure that this is a high variance problem. So even after combining the dev set with the training set, if your error is just came down from 10% to 9%, that basically means that you are overfitting. But let's say you have a different situation here, wherein your human error is 0%, training error is 1%, train dev error is 1.5%, and dev error is 10%. So in this case, we have what we would call as a data mismatch problem, because when you added the dev some of the samples or some of the data from the dev set to the training set, then your error basically so it came down from 10% to 1.5%. Or you can think of that the training error just increased from 1% to 1.5%. So then yeah, these are the conclusions. And so there are no systematic solutions to address data mismatch, but there are some things that you can try. You can carry out manual error analysis to understand the difference between training and dev test sets. You can make your training data more similar, so or collect more data similar to the dev test set. So making sure that your training and dev sets are coming from similar distributions. And if your goal is to make the training data more similar to your dev set, so one of the techniques you can use is artificial data synthesis that can help you get more training data. So you can either combine some of your training data with something that can convert it to the dev or test set distribution. So if, for example, you can combine normal audio with car noise to get audio with car noise example. So just come, so this is an example of making those that train dev set that we were talking about here. So you can combine the noise with the car audio, so then you will get something which is an audio with a car noise example. Or another example is generate cars using 3D graphics in a car classification problem. So that will also add artificial data to your training. But you should be cautious and bear in mind that whether or not you might be accidentally simulating data from a tiny subset of the space of all possible examples, because your neural network might overfit those generated data. So yeah, so you should be very careful about when you are doing um, this kind of jugglery to your training data. And then comes the, okay, so we'll see, yeah. So then comes the concept of transfer learning. So transfer learning is, if you what we say is that we would train a model for a particular application, we can reuse the weights of that model for another application. So people typically what they would do is they would cut out the last layer of the deep neural network, and they would just tune that last layer. And so the initial few layers that is believed to have like to try, it's believed that they are trying to identify some basic shapes or like edges or some like curved shapes. So those are the generic pattern classification layers. You don't need to remove them. You can reuse those weights, and that's, so if you do that, that is known as the transfer learning. So in transfer learning, you apply the knowledge you took in task A and apply it to another task B. For example, if you have trained a cat classifier with a lot of data, you can use the part of the trained neural network to solve the X-ray classification problem. So you can just build a cat classifier model, and you can solve the X-ray classification problem with the cat classifier. And to do the transfer learning, what you have to do is delete the last layer of the neural network and its weights. Option one is, if you have a small data set, keep all the other weights fixed. Just add a new last layer and initialize the new layer weights, and feed the new data to the neural network and learn the new weights. Option two is, if you have enough data, you can retrain all the weights. So some problems are such that you don't have enough training data. For example, if the so the X-ray data is an example of a medical data set. If you just get maybe 100 samples of 100 X-rays, so you don't have the room to train all the weights. So you can just fix all the layers up to L minus 1 if L is your number of layers, and just to tune your last layers. And so option 1 and 2 are called fine tuning, and training on task A is called pre-training. So the what you do on task A is pre-training, and you can intentionally use transform rather than accidentally, and for the problems where you have shortage of data set but you think that the problem is similar. For example, if you're trying to classify the crop from satellite data, so the crop labels are few. We don't get that many